What we're going to do today is we're going to talk a little bit about our next section, kinetics and thermodynamics. We will discuss reaction rates and a little bit of reaction mechanisms. Now, do you think, let me ask you this, do you think that all reactions proceed at the same rate? If you do, you're crazy, because they do not proceed at the same rate. Number one, look at this guy. Hopefully, that is a slow reaction. Because if you buy a new car, do you want that thing rusting fast? No, they got special things. The one I remember, and I don't even know if this is even there anymore, but Z-Bart. You ever heard of Z-Bart? It's like a protective coating that they would put on your car and the undercarriage to prevent the rusting. Okay? So, when that metal comes into contact with the air, it's a slow process of that car rusting. Now, I heard a story of way back when that they had a real small economy car. And I forget what it was because it didn't fare too well in the open market. And the reason is that as the car dealers had it setting on their lots, they're saying, oh man, this thing gets great gas mileage, just a little economy car. It's awesome to drive back and forth to work. Except for it was rusting as they're trying to sell them on the lots. Now, how many of those do you think they sold? Not a whole lot. Because who wants to buy a brand new rusted car? All right. So, rusting. Very, very slow reaction in terms of reactions. Okay? In terms of reactions. Sodium reacting with the air. Now, as I show you this video, it's one we've already seen before, but I just wanted to show it again. We watched this guy when we talked about alkali metals. But when I click on this guy...
Okay, so what else can the sodium react with in air? So if we cut sodium, we should be able to see a reaction. Here is the sodium. And at the moment it looks, well, rather sort of white. Again, if I cut this, I'm just going to stop this using a knife. Much easier to cut than the lithium. And it is, well, initially it's very, very shiny indeed. But already it's beginning to tarnish. So the shiny colour is getting dull, it's becoming dull already. And this is as the sodium is reacting with the gases in the air, not the nitrogen, only lithium can combine with nitrogen. This is reacting with the oxygen, possibly with any water vapour later. So this is forming sodium oxides.
All right, so what we have there, folks, what we have there, ladies and gentlemen, was our sodium reacting with the air. And you could see it was really, really shiny right when he cut it. Now, would you think sodium, because sodium's a metal, and remember we talked about the alkali metals, that they're soft enough to be cut with a knife. What do you think after watching that? That looked pretty soft, didn't it? Like a little firm butter, maybe? Okay. So, yes, indeed. That is a very, very fast reaction. He said it's turning into sodium oxide. It might be pulling a little bit of water vapor from the air. Okay? But that reaction is happening, bam, now. So, rate of reactions, these reactions, chemical reactions, occur at different rates. Now, activation energy is one of the ideas dealing with, I should say, dealing with how fast this occurs. And just explain, this is my activation energy right there. That line from that dash line up to the top of the hill. Now, you should probably have a diagram like this somewhere in your notes to explain what's going on. Here are the reactants. So right here represents the reactants of a chemical reaction. Right here represents the products. Here is energy. All right? And over here, this is time, the course of the reaction. So what I'm seeing, if energy is on this axis right here, the energy of the reactants are greater than the energy of the products. So what is happening is energy is being released here. Now, in order for this reaction to occur, we have to have a certain amount of energy here to get the reactants to change to products. And you can see up top there, that is what we call the transition state. The products, the reactants are transitioning into products. The whole activated complex up there. And at that part, we have neither reactants nor do we have products. We have a combination, the activated complex. Now, this activation energy is the amount of energy needed for that reaction to occur. Now, obviously, if this is a hill, and if I would draw a hill in, let's say I'm going to draw a little dotted hill, that little green dotted hill, do you think that that reaction would be quicker than that red line? Why would it be quicker? You don't need as much energy for that reaction to occur. If you're riding a bike over those two hills, what hill are you going to clear faster? The green one, right? The green one. So, that's some of the deal with how reactions proceed. Now, what affects reaction rates? What affects reaction rates? And I think once we start dealing with this, it's going to sound pretty familiar. How about the effect of temperature? The effect of concentration? The effect of particle size? What's that sound like? Right there. Solubility, right? When we're dealing with solubility, all of those things affected the rate of solubility. Okay? We're going to add one more here. The effect of a catalyst. What's a catalyst? Something that speeds up a reaction. Okay? Something that speeds up a reaction. One of the typical catalysts I like talking about is something that we call catalase. Okay? Usually if you see ASE on the end of some kind of a biological word, that's a biological catalyst. Okay? So catalase we have in our bodies. You remember the lab in biology in which you took sodium peroxide and you put liver in it. And what happened is that liver caused the sodium hydroxide to break down into water and oxygen. So you saw the bubbling. Okay? Did I say hydroxide? I meant sodium peroxide. I think I said hydroxide. Okay? Peroxide. Because obviously you don't want to put sodium hydroxide on a wound if you have it. But have you ever had an open cut and put sodium peroxide on it? Comes in a little brown bottle. You ever done that? Maybe take a Q-tip and rub it on there. What happens? It bubbles. Okay? It bubbles. Why does it bubble? Because it's breaking down to water and oxygen. Why is it breaking down? Because in that wound is something called catalase, a biological catalyst. Okay, it helps to clean out the wound. Maybe you have some dirt in there that you can't even see in that wound. Well, if you put the sodium peroxide on it, it gets down into those nooks and crannies that we can't get to, and it causes it to bubble. Why? Because it breaks it down into oxygen and water. And what do you think that water does? It washes out the wound. Yeah, it washes out the wound. Now, when we talk about reaction mechanisms, here's a reaction mechanism for what we got here is hydrogen gas, and this is iodine monochloride. And we can see that what is being formed is iodine gas and hydrochloric acid. Now, as I look at this reaction mechanism, you can see that I have 2 different transition states, don't I? I have 2 amounts of activation energy. So, this reaction mechanism is 2 different reactions, and we call those elementary reactions. So here's the first elementary reaction, right there. Here is the second elementary reaction. So 2 things have to occur. 2 amounts of activation energy has to occur for this particular reaction to proceed. So it takes 2 different elementary reactions. How do I know how many elementary reactions? How would I know that? What would I need to do? What would I need to do? Jacob? Yeah, if you look up here at the number of transition states right here, how many peaks do you have right there? 2 of them. So how many elementary reactions would be occurring for that reaction to proceed? 2 of them. Now look at this one. Okay? Look at this one. As I'm talking about this, I see 1, 2, 3 different humps of activation energy, don't I? So how many elementary steps is that going to have? 3 of them, right? So that whole reaction mechanism would take 3 steps to occur. So I look at the peaks right here. The peaks right here represent, like we said, the transition states. It's an activated complex. The valley right here at B and C, those are going to be what we call intermediates. Okay? And what an intermediate is it's something that is a product in one reaction that immediately becomes a reactant in another. So I have A here. I hit my activation energy to form substance B, so to speak. Substance B is the product of that first elementary reaction, but now it's going to be the reactant to hit this transition state to form substance C. Well, substance C just become a product, then it's going to go back into another elementary reaction to form substance D, which is our final product. Okay? So we have transition states, we have intermediates, we have activation energy, okay, all dealing with this reaction mechanism. Now, I just told you, I guess I got a little jumpy on my slides because I just talked about what intermediates were. So, let's look at this here again. As I can see, this is 2 different elementary reactions, but right here, those right there are the intermediates that are formed. So the intermediates, we have reactants, intermediates. The intermediates then become the reactants to form the final products right there. Okay?